hiya, 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 hiya. Hi, today I'm going to solve the catenary problem. In most problems that you typically deal with in first year physics, it's safe to neglect the mass of the rope compared to the other objects. But what if the rope is the only object in the problem? Then you can't really ignore its mass. So the problem we're going to try to tackle today is basic clothesline. And the question I have, so let's consider a clothesline that actually has a mass m, and each end makes an angle theta with the horizontal direction. Kind of similar to what I drew here at the bottom of the page. So I've got three questions that we're going to look at. The first question is, let's try to find the tension at the ends of the clothesline. Question 2, or B, find the tension at the lowest point in the clothesline. And then the last part is I want to try to find an equation that describes the shape of the clothesline. Okay. Parts A and B are a little bit easier. I would say typically first year undergraduate level students should be able to solve that. Part C requires a little bit more work and a little bit more calculus. So I would say it's still at the first year level, but it certainly is a little bit harder, as you'll see. Okay, so let's go to the next page and see what we can find. Actually, even before solving the problem, I just wanted to give you some real-life catenary examples. They're everywhere. If you look at anything, a hanging chain, for example, is an example of an object that has mass. It's tied at both ends, and its shape is described as some specific function. You can look at a cobweb. Here, there's a whole series of catenaries. And catenaries don't always have to hang down like this or be concave up. You can have examples where you have an inverted catenary, like the Gateway Arch in St. Louis. Okay, so they're really all around us. You just look around and you'll see them everywhere. So let's look at the actual physics now and see if we can answer our questions. We now consider the clothesline with a mass m, and each end makes an angle theta with the horizontal. Let me just write that in. Pick a different color. Okay, so this is what we have at the end. We're going to have some tension in the rope. Call this T end. And we have that the angle here is theta with respect to the end. And you also have a similar picture on the other side, and with the same angle and the same tension, T end, at the left side of the clothesline. So the first thing we have to do is just write down Newton's laws for this rope. So let's consider a coordinate system here. Call positive x this way, call positive y that way. And the first thing we notice is the rope is in equilibrium. If it's in equilibrium, it means that the sum of the forces in each direction should be equal to 0. Okay, so let's add all the forces in the y direction. Well, in order to do that, we should just do a free body diagram. Okay, so we've got two tensions acting up. We also have, now we have a real rope. Therefore, there's also a force. It has a weight acting down. And the weight is simply the mass of the rope times little g. And that's it. Those are the only forces acting on the system. Okay, so now we can go back and write down our equation for equilibrium. And if we just look at the y direction, in the y direction we're going to have mg pointing down. And we're going to have two forces acting up. It's not tension at the end, but it's a component of tension at the end. And it's also sine of theta. Okay, so here's our first equation. If I isolate for the tension at the end of the rope, I find that the tension at the end of the rope is mg divided by 2. There's 2 ropes. And I also have a term for the angle divided by sine of theta. Okay, so here's our first expression for the tension at the end of the clothesline. And you need this because the total tension acting up must be equal to the weight of the rope in this particular case. Okay. The next thing we have to do is the sum of the forces in the x direction. Now, if you simply consider these forces here, that's not going to be very interesting. You're simply going to have the component of the tension on the right-hand side in the horizontal direction equals the component of the tension on the left-hand side in the horizontal direction. So what we're going to do in order to look at the forces, we're going to split the rope in half. So let's do that. Let's just consider half the rope. Whether you consider the entire rope or the full rope, it really doesn't matter, or just a segment of the rope is in equilibrium. So that means every single part of it is in equilibrium. And we just found what T end was. Okay. And now what I'm going to do is I'm going to introduce a new variable here called T middle. Okay. In T middle, if you look right at the lowest point, it really is only a horizontal force. So let me call that the tension in the middle. Okay. So there you have it. Now, and this whole segment here also has a weight. Okay, but really we've already considered the vertical direction. I now want to only consider the horizontal direction. Okay. So what are we going to have? Well, there's a component of this tension here that is acting horizontally. Right? If we have this angle here, that's theta. This component of the force is T end times cos theta. Okay. So if we put everything together in the sum of the forces, what we obtain is tension at the end times cos theta and now we also have to consider the tension at the midpoint if we're only considering this half of the segment of the clothesline. And put a negative sign because it's pointing in the opposite direction here, and minus T mid. And again, the sum of the forces must be equal to 0 in both directions since the object is in equilibrium. Okay. So you do a little bit more algebra here, and we get that the tension in the middle is equal to T end multiplied times cosine of the angle theta. Okay. I can take this expression just one step farther simply by substituting our expression for the tension at the end. And what we obtain is T mid is equal to the weight mg divided by 2. There's going to be cosine in the numerator and sine of theta in the denominator. So if I combine both of those, I'll get tangent of theta. And here's my expression for the tension in the middle of the rope. Okay, so there's the solution for part A. And at the lowest point, that's the middle of the rope, or the middle of the clothesline. There's the answer for part B. Now let's look at a few limiting cases of this expression and see what happens. Okay, let's go to the next page and do that. Okay, now I want to look at a couple limiting cases. Let's consider the case where the string is connected to the end, except it makes an angle of, oops, it's not drawn very good, but it makes an angle equals to 90 degrees. as in this case, with respect to the horizontal. If you take that limit, what you're going to find is that the tension at the end is equal to mg divided by 2, and you get 1 over sine of 90, which is equal to 1. Okay. Now what happens for the tension at the midpoint? Tension at the midpoint, again, equals mg divided by 2. 1 divided by tan of 90. Okay, well, tan of 90 is sine of 90 divided by cos of 90. Sine of 90 is 1. Cos of 90 is 0. So the tension at the middle point is 0. So the tension kind of varies from half the weight on each side. It has to be equal to half the weight on each side because it has to support the total weight of the object. And the total weight of the object is simply mg. So you have Tn on this side and Tn on this side acting up. Okay. So there's a kind of an interesting limit, and the tension at the middle point should be equal to 0 in this limit. The other case you can consider is what happens when the angle theta equals to 0. Okay. So what would that picture look like? And remember, that's the angle with respect to the horizontal. Okay, so the angle equals 0. It basically looks like a horizontal string. But we have to remember that this object here still has a weight. Okay. Right. If I just put the weight at the center of mass of the clothesline, what's the condition that I would have for the tension in order to have this condition, right? So you have T at the end, which is in this direction, and T at the other side, which is the same. If you substitute 0 in our expression, what do we get? Well, you get that the tension at the end and mathematically what happens is, well, if you substitute 0 into this equation, you basically have a division by 0. Or you have that the tension tends toward a very, very large number. Okay. And what about the middle point? Okay. T middle. Again, T middle is also, you're also going to run into a problem because you also have a division by 0. Okay. So T middle would also tend toward infinity. It's basically stating the point that you run into really big problems if you have 0 angle. And in practice, you cannot have 0 angle. You'd have a very, very large tension in the rope in order to satisfy that because we're dealing with a real-life object, and the angle might be small, but you need a component of the tension that is vertical in order to support the weight of the object. Okay. Continuing on to calculating the shape of the catenary, I want to first just illustrate a case where instead of considering this half segment of the clothesline, what would happen if I broke it down into a number of segments? Okay, in this case, I'm just going to consider 3 segments. So, if you break the rope down into 3 segments, and if half the weight of the rope is mg divided by 6, mg divided by 2 rather, that means that each one of those segments is going to have a weight of mg divided by 2 and multiplied times 1/3. Okay. So now let's split these up a little bit so we can look at the forces acting on each segment. Okay. Let me separate them out a little bit. Okay, so we've got this segment here that's near the bottom. we're going to have another segment that's starting to kind of curve up. We've got this segment here, which is kind of our last one, and where we have the end connected to the wall. Okay, so we know that there is T end, and we also know that the clothesline was making some angle theta at the end. Okay. However, you see that the angle is not uniform. Okay? If you consider this segment over here, well, there's going to be some tension. Let's call that T1 here. And this angle is certainly different from that angle. So I'm going to call this angle here theta 1. There's also another force over down on this side, right? So tension force over here. And again, that angle is getting pretty small. Let's call that angle theta 2 with respect to the horizontal. And I'm going to call this force tension T2. Now if I break the rope down into segments like these, each one of these tensions has a action-reaction pair. So it has to have a force in the opposite direction, but the same magnitude, and it's acting on a different object. So let me just finish this diagram here. So I also have to have T1 at that, and the angles are the same. If theta 1 was the angle with respect to the horizontal for this force, it's also going to be the angle with respect to the horizontal for this force here. Okay. And I can't forget at the end, or at the middle of the clothesline, I still have this. I still have T mid, which is basically just the horizontal component. Okay. Now for each one of these segments, you can write an equilibrium condition. For each one of those segments, I have to have that the sum of the forces in the x direction must be equal to 0, and I have to have that the sum of the forces in the vertical direction must be equal to 0. And I can do that equilibrium condition for every segment, so I can write down 3 equations. Okay. If I look at the first segment over here, well, this one here tells me that the tension in the middle of the rope must be equal to T2 cos of theta 2. Okay. I must also now, if I look at the horizontal forces for the second segment, I'm just going to stagger these a little bit. What I would find would be that T2 cos of theta 2 must be equal to T1 cos of theta 1. And if I look at the last segment over here, I would find that T1 cos of theta 1 must be equal to the tension at the end times cos of that final angle, which I'm just calling theta. So you can see that if I combine all of these equations together, the expression I get, I could substitute T2 cos of theta 2 with T1 cos of theta 1, and then I could substitute T1 cos of theta 1 with the tension at the end times cos of theta. And I'm left with the same expression that I had if I simply looked at the sum of the horizontal forces on half of the clothesline. Okay, and that was the same expression. T end cos of theta. All right, that's the exact same equation that we previously saw. Okay. Now, if you look at the sum of the vertical forces, I can also do that. If I look at the first segment, let's just call the weight, instead of me writing 1/3 mg divided by 2 for each segment, I'm just going to call this weight here small w. Okay. So let's look at all the forces acting in the vertical direction for each segment. If I look at segment 1, I'm going to have that the force acting up, simply T2 sine of theta 2, and that there has to be equal to the weight of that segment, W. Okay. If I now look at section 2 over here, and I add all the forces, well, there's 3 forces I have to add. I have to add the components of the tension, Okay, so I'm going to have T2 sine theta 2, that's acting down, plus W must be equal to all the forces acting up. That's T1 sine of theta 1. And now we repeat the same steps for the last segment. And what do we find? All the forces acting down. We have T1 sine of theta 1. We also have the weight. Okay, I should include that in the diagram here. It's the weight of that segment. And that there has to be equal to the tension at the end times sine of that final angle. Okay, so what can you do now? Well, I can get rid of T sine of theta 2 into this equation because that's simply equal to the weight. And then I can get rid of T sine of theta 1 and substitute that over here. And what you end up getting is 3 times small w is equal to T end times sine of theta. Now remember, there's a 3 here because it's simply the weight of each individual segment. So actually, if you substitute everything in, you get 3 times a third, which cancel out, and you're left with mg divided by 2 is equal to the tension at the end times sine of theta. Okay. And this is exactly the same expression we had when we looked at the entire rope. Okay, so whether you break the rope down into a finite number of segments or you consider the whole rope, when you look at the sum of the forces, you're going to get the same answer. So I just wanted to highlight that point. Okay, for the last part now, we're going to try to find an equation that describes the shape of the clothesline. So I've just sketched out half the clothesline here with the quantities that we've already found, the tension at the middle, tension at the end. However, now what I want to do is I want to consider a point somewhere along the clothesline. Okay. And if we're just going to consider this segment over here, this segment here has a certain length. Let's just call it S. Okay, and the total clothesline had a mass M, and let's just say it has a length L. And the mass of will be uniformly distributed along the clothesline. So that means there's a linear density, which is called mu, and that's a constant. So it's simply the total mass divided by the total length. So if you want to know the total mass of just this segment, well, all you have to do is simply multiply the linear density mu times the length of the segment. Okay. So that also means that the weight of this guy will be the mass of the segment times little g, and the mass of this segment here will be this quantity, the linear density, times the length of the segment times little g. Okay, that's the total weight of this guy. Now, if we're just looking at this segment, well, at that particular point there's going to be some tension. Okay, I'll just call it T. And tension here, and this is going to be some position that has a coordinate x and y. Okay, now if we go through, again, we go through the same exercise as we previously did. If we do sum of the forces along the x direction, well, again, just looking at all the forces acting on this segment, we're going to have, and let me just call the angle over here, let's call that angle with respect to the horizontal, the angle phi. Okay, so we have T mid which should be equal to T cos of that angle. And if you look at the sum of the forces along the y direction, again, it's only this component of the tension here that has a vertical component. And that there has to be equal to the weight. And if I just wrote the weight in terms of that linear density times the length of the segment, this here has to be balanced by that vertical component, which is t sine of the angle phi. Okay, and to simplify this just one more time, let's just call this equation 1 and call this equation 2. Really what I want to do now is just get rid of this tension. Okay, and I can get rid of the tension, say, by taking equation 2 and divided by equation 1. Okay, if you do that, you're going to get mu times s times little g divided by t mid is equal to tangent of this angle phi. So this is kind of an important equation here. And just to simplify things a little bit more, I'm going to introduce a constant. Okay. I'm going to call the value a. I'm just going to be equal to t mid divided by everything here. And you'll see why I do that in a minute. I just want to simplify all of the expressions that I'm going to have. Actually, sorry, I'm not going to include the segment length there. I want to introduce a parameter a that has units of length. So now if I rewrite my equation here in terms of this new parameter a, I get that the tangent of that angle somewhere along the rope, okay, tangent of this angle phi is equal to, I'm still left with that segment length s, and I've introduced this other parameter a, which also has units of length. Okay. This is basically the fundamental equation that describes the shape of this rope. Now we'll have to go and do a little bit more calculus and a little bit more math in order to simplify this, but this will be our starting point now, that the tangent of this angle equals to the length of that segment divided by a. And a is a parameter of the linear density of the rope, of the tension at the midpoint, and so forth. Okay? So let's go to the next page and continue along this line here. Okay, so we now have our expression that the tangent of the angle phi, which is the angle that the rope makes at some position xy, is equal to our length of our segment s divided by this parameter a. So now we want to introduce x and y coordinates, because at the end of the day, really what I'm looking for is I'm looking for a function of y as a function of x. And I certainly don't have that now. Okay. So the first thing to notice is that I can introduce the spatial coordinates x and y by noting that the tangent of a curve, okay, the tangent of a curve is simply equal to the derivative of that function at that specific point. Okay. So there you go. Now I've introduced x and y. Now the other thing to notice is that the length of this segment here, well, if the segment is very, very small, let me call it ds. Let's consider the length of an infinitesimal segment here. And if it's really, really small, the length of that segment is approximately going to be given, you can just use just a standard triangle. And if the angle, or if that segment is small, what you end up doing is everything will be small. So this will be some small element dx. This here will also be some small element, call it dy. And what you do is you just simply have a right angle triangle there. So ds is simply equal to square root of dx squared plus dy squared. Now if you factor out a dx term, what you're left with is 1 plus dy over dx. That's getting a little small. I'll clean that up in a second. Don't forget to square that term. And finally, we're left with ds over dx. And let me just rewrite this as the square root of everything here. 1 plus, we get to square that, dy divided by dx. Okay, now if I go back to, this is equation 3 here. Let's call this equation 4. Now, if I want to substitute or combine equation 3 and equation 4, I first need to take the derivative of equation 3 with respect to x. So let's do that. If you differentiate equation 3 with respect to x, you get second derivative of y with respect to x is going to be equal to 1 over a at parameter times ds divided by dx. And now what you can do, well, now you simply substitute in our expression for the ds over dx. Okay. dy over dx squared. And there you have it. Now we have a differential equation. We have the second derivative of y with respect to x is equal to 1 over a times the square root of this complete term here. Okay. In order just to simplify this a little bit, let me introduce just some shorthand notation. Let me just call p is equal to the derivative of the function y with respect to x. And I could simply rewrite this equation just to simplify it a little bit. This equation simply becomes dp divided by dx. And this is simply equal 1 over a square root of 1 plus, this term here is simply p squared. Okay, now it's much kind of friendlier looking equation than what we previously had. Okay, so let's continue this calculation, and we're just about done now. All we need to do is find a solution for this equation for p, and then we should be able to use just basic calculus and find the equation for y as a function of x. So this is the last expression we had. So in order to solve this, what you do is you first group all the terms that have p. dp divided by square root of 1 plus p squared is going to be equal to 1 over a times dx. Okay. And what you're doing after that is you're simply integrating both sides. Okay. So this right-hand side is very simple, a constant, nothing happens. You're left with x. So this guy over here, this one's a little bit more complicated. And I'm not going to solve that here, but what you do is you just look it up in a book. This is kind of a standard problem for indefinite integrals. And the solution is simply the natural log of p plus and the square root of the same thing. Okay. Now, since these are definite integrals, I also have to add a constant. Let me just add it on the right-hand side here. And let me call it constant C1. Okay, so we're left with the natural log of p plus square root of 1 plus p squared is going to be equal to x divided by a plus some constant. Okay, so the first thing we need to do is let's find the constant. Okay, and remember what our value for p was. P was simply that derivative of the function y with respect to x. Okay, and one thing we know is that when x equals to 0, you have to remember the shape of the catenary. If you take x equal to 0 as the midpoint, when x equals to 0, the derivative should also be 0. Okay? So dy divided by dx is equal to 0, or p is equal to 0 at that point. Okay, so if p equals to 0, you see here you're left with ln of square root of 1. X is equal to 0. Substitute everything into this equation, you find that the constant c1 that we introduced from this indefinite integral must be equal to 0. Okay. So one last step, I can just simplify this and eliminate that constant. Now this still looks pretty nasty, but we can simplify this expression. To simplify a natural log expression, one of the simplest things to do is just take the exponential of both sides. And if you do that, you're left with 1 plus p squared equals exponential of this entire term, x divided by a. Okay. And now in order to simplify this a little bit, we really want to get rid of this square root term. And what I recommend is simply isolating that term. So let's bring p to the other side. Okay. So you're left with square root of 1 plus p squared equals exp of x over a minus p. And now what I'm going to do is I'm going to square both sides. Okay. So let me just bring everything over here. If I square the square root, that just kind of eliminates that. And I'm left with 1 plus p squared is simply equal to, now you got to square everything here. So we get exponential, squaring that first exponential simply means, plus 2x over a, still positive, minus 2 times exp x over a times p, and plus p squared. Okay, luckily for us, the p squared term is on both sides. I can just get rid of it. And now if I just do a little bit of algebra, I can bring this over to the other side and then divide by 2 times exponential of x over a. And I'm left with one final expression for p, and that p is simply equal to 1/2, open a bracket, exp x over a minus exp of minus x over a. Okay, and there you go. So you have an expression for p, and remember what p was. P was the derivative of y with respect to x. Okay, now let's go to the last page and just finish this up here. Again, we have one more step. We simply have to integrate this formula because the goal at the end was to find an expression for the shape of the catenary. And the shape of the catenary is a function of y as a function of x. Okay, that's really what we want. And right now we have an expression for the derivative of y with respect to x. But it simply involves 2 exponentials. This is very easy to integrate. So let's go to the next page and get that done. We know that the derivative of y with respect to x is equal to this term. You should be able to write that the expression for y as a function of x is equal to simply a divided by 2. And this becomes, this is the same, x over a. And when you integrate this, this term becomes plus minus x over a. and curly bracket to close that off. Now again, I'm integrating. I should also introduce another constant from the integration, something like this. Now if I go back to the catenary, let's find the value of that constant. So again, now it's just a matter of picking where we want to center the catenary. So let's assume that when x equals to 0 at this position, that this bottom position is also equal to 0. Okay. So the bottom here is at 0, 0 coordinate. Okay. So if you substitute 0 into this expression, we are left with a over 2. What do you get? You get 1 for this one, plus 1 for the other one, plus C2 equals to 0. Therefore, C2 should be equal to minus A. Okay? So the last thing you should notice too, the sum of the exponentials. Okay. This is a hyperbolic function. Okay. You remember from calculus, hyperbolic cosine is equal to 1/2 the exponential of the value x plus exponential of minus x. Okay. So if you group everything together now, I can write our equation for the catenary, y of x in terms of this hyperbolic function. Okay. The first term is simply a. I'm left with cosh of x over a and minus 1. Okay. Here's the final expression I have for the catenary. Now I can't forget what the value of a was. A was a constant that I had introduced. A was simply equal to the tension in the middle divided by the linear density times little g. Okay. Now if you went back and you substituted in our expression for tension in the middle, you would see that this expression can simplify to simply the length of the rope divided by 2 and times 1 divided by tangent of theta. And now you see that it really does have units of lengths. Okay. So there's the final expression for the catenary. It is a hyperbolic cosine function. It is not a parabola, although parabola is not really a bad approximation to that curve. So let me open up a graph window and let's have a look a little bit more at the shape of this function here for a typical value of the angle theta. Numerical example just to apply the equation that we just derived. So here's my catenary. I'm going to assume that the total length of the clothesline is just 1 meter and that the angle it makes at the end with respect to the horizontal is going to be 30 degrees. Now if you remember that parameter a that I had found, a was simply equal to the length divided by 2 times 1 divided by the tangent of the angle. Okay. And, well, we need the tangent of 30. Tangent of 30 is simply sine of 30 divided by cos of 30. And sine of 30 is 1/2. Cos of 30 is square root of 3 over 2. So tan of 30 is just 1 divided by the square root of 3. Okay, so I can substitute everything into this a parameter that we have, We have 1/2 at the beginning, and 1 divided by tan of 30. So the square root of 3 ends up coming to the top. So therefore, a is simply going to be equal to square root of 3 divided by 2. Okay, we needed that parameter a because that parameter a is in the equation for the catenary. All right, we had a, open bracket, hyperbolic cosine of x divided by a minus 1. And we're also going to look at the derivative of this function. The derivative of a hyperbolic cosine is simply a hyperbolic sine function. Of that same argument, x over a. Okay, so I now want to find if this whole length is 1 meter. Right? I know how long the clothesline is. I can easily measure what the angle that the clothesline makes with respect to the horizontal at the end. So the question is, how far does it kind of dip down? Right? What is this y value? Okay, and you simply have to solve this expression here. And you want to solve it, though, for which the value of the angle is 30. I don't want to just extend this function all the way to infinity. I have to know when I'm going to truncate this function. Which value of x do I truncate the function? And I'm going to truncate the function when the derivative, or the slope, remember this is tangent of the angle, when that there equals to tan of 30 degrees, okay? Or 1 divided by root 3. Okay. So you first need to find for which value of x does the derivative over here equals to tangent of 30 degrees. Now once you find that value of x, you can substitute that value of x inside our equation for the catenary, and then you'll be done the problem. Okay, so I'm going to now open up Desmos, and we're going to plot some of these functions. Okay, so I now want to look at the equation of the catenary for that one specific case. So we had a length equals to 1, and we had the angle at the end of the clothesline with respect to the horizontal was 30 degrees. Okay, so I open up the Desmos window here. It's just a graphing calculator. I've defined the function, which is what we found in the previous case. Let me show you what that looks like. So here's our catenary. Now it extends really far, right? I didn't really give it any limits just yet. So this length will be much larger than 1. Okay. I also now want to show you that, remember what I told you. I said that the angle was 30 degrees with respect to the horizontal. So we have to find at which point on this curve is the angle 30 degrees. Okay. Well, we know that we could start by plotting the derivative. That's the derivative of this, of the blue line, okay? This purple line here. And this is the derivative. This is also the slope, right? And really what we wanted was, we wanted the slope equal to tangent of 30 degrees. Okay. And tangent of 30 degrees, we evaluated on the previous page, that was 1 divided by the square root of 3. So let me go ahead and mark that point also. So actually, this is the value of x that we're looking for. It's where we have an intersection between tangent of 30 and the derivative of our catenary. Okay, so really we want is 0.0476. So let me just write that down. We want x equals to 0.476, and we really want x equals to minus 0.476 as well. Okay. And at the end of the day, let me get rid of that. Let me get rid of this now. Really all we're interested in is plotting this catenary as a function of position, but we really don't want to include anything outside of this range. Okay. At these points here, this is where the angle equals to 30 degrees. You can go ahead and measure that. And we also require that the total length of the catenary should be equal to 1. And now, well, this almost looks like it would be close to 1, right? You're not quite going up to half a meter on each side, so that's good, right? We know that that kind of physically makes sense. The other question I wanted to know is how far does this catenary drop? All right. So all we need to do is find the value of y when x equals to 0.476. So let me just go ahead and evaluate that value. 476. And what do we get? We get y equals to 0.134. Let me go ahead and write that down too. Y equals to 0.134. So there we have it. When we have a length of 1 meter, okay, and the angle of the catenary makes an angle of 30 degrees with respect to the horizontal, we're going to have that the middle is 13.4 centimeters lower than the end. And that'll also ensure that the total length of the catenary, or the total length of the clothesline in this case, is 1 meter. Okay, so let's go back to the other page and just fill that out. So we find that in this specific case, y should be equal to approximately 0.134 meters. Okay, and there's the solution. So there you have it, folks. There's the catenary example. I'm going to post the PDF of the full solution here on my website, so don't worry about taking notes. Okay, so the next time you're walking around and you see a hanging chain or a clothesline, you can turn to your wife or your husband and say, there you go, look at that catenary over there. You kind of learn to kind of appreciate it at a deeper level. Right? You know that the shape now is a hyperbolic cosine, not just a simple parabola. It took a little bit more work, and simply by measuring the angle at the end and knowing the total length of the rope, you can almost define the entire shape of this catenary. Okay, so it's kind of a rather nice problem, I find. It's a lot of work, but hopefully I've described the steps in a way that everybody can understand. Okay. Thanks for watching.